Hi, welcome back. We're in Lecture 12, Segment 2, and in this segment I'm going to talk about dummy coding. It's necessary to talk about dummy coding in the context of the general linear model to show you how categorical predictors are handled in this framework, and we also use it as we move forward in more complex multiple regression analyses like moderation, which will be the topic in Lecture 13. So let's examine how dummy coding works. So dummy coding is conceptually real easy, but it's sort of a tedious process and students sometimes get tricked by it. So conceptually, it's real simple. It's just a system to code categorical variables in a regression analysis. So I'm going to use an example here, sticking with this sort of faculty salary example. Imagine that we had a categorical predictor that we wanted to add into that analysis. And imagine that that categorical predictor is what area of research a psychology professor engages in. So typical psychology departments, they have some cognitive psychologists, some clinical psychologists, some social psychologists, and so on. So imagine I can just code each professor according to one of these areas or groups, and then look at the number of publications that they have. So that's my dependent variable or outcome variable in this example. Your data frame might look something like this. We could have a professor ID, like the initials of the professor, what group they're in, cognitive, clinical, developmental, whatever, and then the number of publications that they have. So assume these are like senior professors. It's a lot of publications. So toward their end of their career. How are we going to code this if we wanted to run it in a regression analysis, for example, using the LM function in R? We can't put group into the LM function because that's a character variable or a string variable. We need to make it a numeric variable in some way. So that's where dummy coding comes in. This is a simple scheme to put a numeric value on each of these groups, and I'm using cognitive as what's called the reference group. And I did that because I'm a cognitive psychologist, so for me that was easy to remember that cognitive is going to get zeros across the board for dummy code 1, dummy code 2, and dummy code 3. So why do I have 3 dummy codes? Well, because I have 4 levels of my independent variable or my grouping variable. It's always the number of levels or number of groups minus 1. And you make one of your groups the reference. And I decided to make cognitive the reference just because I'm in cognitive. And then you just code each group with a 1 for one of the dummy codes. So the clinical group got a 1 in D1, the developmental in D2, and social in D3. This may look a little bit odd, and a lot of students, they tend to think that you need 4 codes if there's 4 groups, but remember it's always the number of groups minus 1. And if you think about how the regression equation works, this might start to make a little bit of sense. Now remember, what's the regression constant in a multiple regression? It's the predicted score on the outcome variable when all the x's are 0. Well, I now have a really meaningful group there. I have the cognitive group. That's all x's are 0. So my regression constant is going to be the predicted score for the cognitive group. So let's see how that works. I would just add those dummy codes to my data frame. So now I have a larger data frame. I have 3 more columns. So this is what it would look like in R. Then I could run the LM. Before I show you the output of that, I just want to show you the summary statistics so you know what to expect. So it looks like the cognitive group has a mean of about 93 publications, clinical less than that, about 60, developmental a little more, 103, social a little less, 70, and so on. There's the standard deviations. And also notice that there's a different number of professors in each group. That's going to be important in a moment. So the regression model would look like this. We just put in the 3 dummy codes. So now we have 3 predictors. And this will allow us to look at all these pairwise comparisons between groups. And here's what the output looks like. So this first number here is the regression constant. That's the predicted score when all x's are 0. So that's the predicted score for cognitive. If I go back and look at the mean for cognitive, it was 93.31. And that's exactly what I get for the regression constant. It's the mean for cognitive because I made cognitive the reference group. Now, what is a negative 32.64? What does that mean for clinical? Well, it's a 1 unit increase in x is associated with that much of a predicted change in y. Well, a 1 unit increase in x took you from cognitive to clinical for D1. So that means clinical has, on average, 32 publications less than cognitive. And if you look back at the summary statistics, that's about right. Developmental had slightly more than cognitive, 10.19, and social had less than cognitive, 23. And you might want to ask, are those differences significant? Well, then you just look out here to your p-values, and you can see that the difference between clinical and cognitive is significant. The difference between developmental and cognitive is not significant. And the difference between cognitive and social is significant if we're using 0.05 as our cutoff, which is standard. Now you might want to know, well, I want to compare, say, developmental to clinical, or I want to compare clinical to social. So if you wanted to do that, you would have to change your reference group and rerun this, which is why we typically don't do this. We don't take this approach if we're just looking at one categorical predictor and these pairwise comparisons. I would do a one-way ANOVA instead. But this is a way that you can code a categorical variable in a multiple regression analysis, because as you'll see next week when we do moderation, we're going to have some of our predictors are categorical, some of them are continuous, and then we want to put them together in a moderation analysis. We have to have this sort of coding scheme. You might also want to change it so that this number is not the predicted score for cognitive, but just the predicted score for all professors across all groups. That, if you want to do that kind of coding, it's called effects coding. The first effects coding I'm going to show you is unweighted, and then I'll do a weighted effects coding. So effects coding, you'll see I still took cognitive as my reference group, but you'll see now I gave them -1s across the board. And then for the rest of the codes, which I'm calling C1, C2, and C3 now to call them effects codes instead of dummy codes, now you'll see, well, what's the predicted score when all x's are 0? Well, it doesn't represent any one group, but what it does represent is the average across all these groups. So if I run that and look at the coefficients, now what's changed is the regression constant. It's 81.9. If you look back at the summary statistics, the mean is about 81.6. So it's not exactly the mean for the entire group. And the reason for that is it's unweighted. It doesn't take into account the fact that there are a different number of professors in each group. So in a second, we'll do the weighted effects coding, and that would get us the exact mean, 81.69, I think it was. But now, what do these regression coefficients tell me? Well, this one is the difference between the overall mean and clinical, and this one is the difference between the overall mean and developmental, and so on. And again, if you wanted to know the difference between the overall mean and cognitive, then you would have to recode this with a different reference group. And again, if you were just looking at this, this example and you just wanted to do, just ask this question, are the number of publications different across these groups, then you wouldn't do this sort of clumsy dummy coding or effects coding. You would just run a one-way ANOVA. Again, we need this system when we have examples like we will cover next week, where we have some categorical predictors like this one, like group, in the same model as continuous predictors like years since PhD or number of publications. And then if we want to look at those two predictors together in one model, we're going to have to come up with this demi-coding scheme. So finally, the weighted effects coding. If you wanted to get that regression constant to be the exact mean of all the professors, then you would just have to weight each of them by the number of professors in each group. So instead of -1, it's just -n for number of professors in the clinical group divided by n number of professors in the cognitive group, and so on. Just do instead of -1, just do these fractions. And that would get you the exact mean, which is just slightly off of 81.9. I didn't actually run that one, but I wanted to show you exactly how you would do that. And if you ever come across a situation where you needed to do that, that's weighted effects coding. So to wrap this up, it's, again, conceptually really simple. It's just you have categorical variables that are nominal, so you can't throw them into the GLM or into the LM function in R because they're string variables. So you have to make them numeric in some way, and the classic way of doing that is called dummy coding, where you just pick one level of your independent variable or your categorical variable and make it the reference group. That one gets all zeros across all the codes, and then you have just as many codes as groups -1, and that's it. And that allows you to look at categorical predictors in the same model as continuous predictors and put them together in moderation analyses, which is what we're going to do in lecture 13.